Frank T. Kite, Center for Astrobiology, Institute of Geophysics and Planetary Physics, University of California, Los Angeles, California, 90095-1567 USA. You can reach him at kite@igpp.ucla.edu. Distal impact spherules provide information about impact processes that cannot be perceived by analyses of impact craters or numerical models. Two rather well-studied impact spheral deposits, which are also relatively well preserved, are the KT boundary and the late Eocene deposit containing clinopyroxene-bearing spherules. The KT boundary spherules are almost certainly directly related to the Chicxulub impact event, and the late Eocene clinopyroxene spherule deposit is commonly believed to be derived from the Popigai event. These are the two largest impact structures in the last 100 million years. These deposits have several common features, which may reflect processes common to large body impacts as well as significant differences. I will concentrate on data from the KT boundary at DSDP Site 577 Western North Pacific and Eocene ejecta from ODP Site 709 Western Indian Ocean. The KT boundary is known to have at least two distinct spherule deposits. Large glass spherules are found beneath impact wave deposits of the Gulf of Mexico and are commonly attributed to impact melt from low-velocity ejecta that has a very low extraterrestrial component, that is, low iridium content. These are probably distributed regionally and not globally. They form the lower layer of the KT boundary couplet in the western interior, North America, and traces of large hollow spherules found in North Pacific sites GPC3 and DSDP 577 may also be from this source. The iridium-rich global fallout is also composed mostly of spherules. Its origin is probably largely from the impact plume, but may also contain materials derived directly from meteoritic materials. The KT boundary is known at well over 100 sites. The mean amount of iridium deposited is on the order of 55 nanograms per square centimeter. The KT boundary at DSDP 577 probably has the best preserved spherules of any site. However, in nearly all cases, most of the silicates have been replaced by clay minerals. So bulk chemical analyses of the original major element chemistry are impossible. The high degree of preservation is probably related to shallow burial at Site 577, 109 meters, and oxidizing rather than reducing conditions following burial. Three high-temperature minerals have been identified at this site. Clinopyroxene, found only at Site 577, may be the precursor to diagenetic sanidine in some European sites. Magnesia ferritis spinel has the highest Fe2O3/Fe of any KT locality and can have trace inclusions of Ni-rich magnesia wustite, which is known at only one other site, Site 596, South Pacific. Other debris described include shocked quartz grains greater than 200 micrometers, hollow spherules possibly related to regional glass deposits, and irregular iridium-rich particles that may be unmelted meteoritic materials. The latter may be related to the fossil meteorite found at DSDP Site 576, just 500 kilometers to the east. A large volume, approximately 10 cubic centimeters, sample from DSDP 577 provided a 44 milligram carbonate-free residue, greater than 60 micrometers, composed nearly entirely of impact debris. Nearly 2,700 particles greater than 100 micrometers were classified based on color, shape, and morphology. Although they form a rather complex assemblage of spherules and other particles, they can be generally described as about 60% light-colored spherules and about 40% dark-colored spherules. The light-colored spherules are mostly white but can contain dark inclusions, and several percent of the total include green, clinopyroxene-bearing spherules and fragments of large, hollow spherules. These have generally low siderophile element concentrations, iron, chromium, nickel, cobalt, iridium, and are probably derived from a target-rich portion of the impact plume. Many were found to have pseudomorphic textures similar to the dendritic textures of clinopyroxene spherules, so it's likely that many, if not all of these, are altered from high calcium pyroxene. The dark-colored particles have a broad range of siderophile element concentrations, but are generally more enriched in the meteoritic component than the light spherules. As noted by some researchers, some of these particles have iridium concentrations comparable to those found in chondritic meteorites. The dark particles invariably contain magnesia ferrite spinels, but the sphenol content is quite variable, ranging from trace concentrations to perhaps 50% by volume of some spherules. A small fraction with high iridium have irregular outlines and no obvious melt textures. These are the possible unmelted meteorite particles described by Robin et al. Hypotheses for the origin of the sphenol-bearing spherules include origin in the projectile-rich portion of the impact plume, or as a form of ablation debris derived directly from meteoritic material. Possibly both are important sources of these particles. We have found several light-colored spherules with dark inclusions that are a mixture of the two main spherule types, with one or more inclusions of spinel-bearing material. We believe that this indicates that both types of material coexisted as liquids, strongly supporting a plume origin for at least some fraction of the spinel-bearing spherules. The late Eocene clinopyroxene spherule deposits contain a similar mix of particles to those in the KT boundary. They are much better preserved, commonly containing glass and unaltered clinopyroxene, so it is possible to determine bulk major element chemistry of the precursor materials. As with the KT boundary, there are two distinct components: a glassy microtectite that may be equivalent to the impact melt glasses of regional KT deposits, and the clinopyroxene spherules that are distributed globally. Isotopic analyses of these components have shown that the microtectites and clinopyroxene spherules are from the same source, and this is consistent with the Papau crater. Iridium analyses have been reported for 12 sites, and the mean iridium deposited in the late Eocene was on the order of 9 nanograms per square centimeter, or about 16% of the KT value. A large volume sample from ODP Site 709 has yielded more than 17,000 clinopyroxene spherules, and several hundred microtectites greater than 125 micrometers, as well as shocked quartz and coesite. The microtectites have a very low siderophile content, less than 100 picograms per gram iridium, while a bulk sample of the clinopyroxene spherules has about 1 nanogram per gram. Analyses in progress. As with the KT boundary, there are both light and dark-colored clinopyroxene spherules. Microprobe analyses of these spherules indicate that the main difference is that the light spherules have generally high calcium oxide, 12% versus 6% on average, and lower iron oxide, 3.6% versus 7.5%, and probably also lower chromium. But chromium data are near detection limits and imprecise. In general, this is consistent with a model in which the clinopyroxene spherules are from the impact plume, with the darker spherules from the more projectile-rich portion of the plume. Unlike the KT boundary spherules, sphenules are never more than a trace phase in the clinopyroxene spherules, but they are clearly more common in the darker spherules. Compared to the KT boundary, a significant component appears to be missing in the late Eocene deposits. The coarse fraction of KT deposits holds the majority of the IR and other siderophiles in well-preserved deposits like DSDP 577. But in the Eocene sediments, the IR in the CPX spherules can only account for a small fraction, at most a few percent of IR in the bulk sediment. Whether the principal IR carrier is an ejector component in the fine fraction or some larger IR component that is not preserved in sediments has yet to be determined. Reference Smith J.